Okay. So here we are, Thursday, the 14th of January. Announcements. The only thing I have really for announcements is that I've changed a little bit the way that I'm doing the calendar on the home page of the Canvas. That should be the first page you see when you open it up. It should go right to the home page. And on there, you'll see announcements and you'll see a calendar, and then you'll see a link to the modules. That's really all you should have to mess with in Canvas. Keep it simple, right? So on the calendar now, I'm going to blow up the week we're in. I'll blow that up. So that's what this is, and it has what happens in the day, and then what happens in the evening. Okay, so the assignments. So the only thing new here is I'm trying to be as detailed as I can on these assignments. Like today, tomorrow, your tasks. And your tasks and in-class tasks are the same, except that you don't do stamps. So like you would do hand and paper a week if there's enough stamps out there to make up for the stamps. So it's a similar assignment. Okay, but the other new thing is every time I post a key, you'll have this maroon with white lettering in that night. So like 4.1 was posted on Monday. The light blue is sample problems are being added. And then this is 4.2 key will be posted today, this afternoon. I'm waiting on that because yours was due last night. So I'm waiting for you to turn it in today if you haven't. Most of you have. And this is for 4.2. Then I'll post a detail key this afternoon. Okay, and then this weekend I'll post a key to 4.4. And that you're not going to turn in 4.4. You're not going to submit 4.4. You'll turn it in later, but you're not going to submit it. And then this is the next 2 weeks, kind of my best guess at the next 2 weeks. Looks like we are going to do a flex day on the 27th. I don't think that'll affect you at all. The only way that's going to affect you is it's going to move our normal meet time is 1:10. On that day, I think it either moves it up or moves it back a little bit, and it shortens it. So on a Wednesdays, if we're doing a flex day, it'll have a slightly shorter, it won't be 50 minutes, it'll be like 40 minutes on that day or something. So, and it'll slightly change the start time, but not much. Okay. That's your announcements. Friday, that's for the in class. There's the practice problems. I know that you're already asking questions. Sophia saved my bacon on, I've changed this now because she pointed out that there was no height given for the Harv. And I guess I was assuming that they knew the height from when I wrote this question. It's 11.1 meters is the delta. That's your height of the Harv, 11.1 meters. And that's in the new, when you go to Facebook, the question that's been replaced has that in there. But I gave her a couple of Facebook points for finding mistakes. Any mistakes you find is worth 2, at least 2. Okay, so people have asked about this one, and I responded, and then Sophia asked about that one, and keep asking. Because this coming Monday, I'll post the next 6. All right. You don't want these to start piling up on you. You want to stay ahead of them or stay in line with them. So it's probably 2 a day. Do 2 a day. Just try 2 a night. Now, eventually, the key is posted. So how sloppy your work is doesn't matter. You're not really turning it in. You're turning in your notes, and in your notes you'll get credit because it'll take up pages. But I will post at least a detailed key for each problem. And hopefully there'll also be a help video attached to it as well. So you're going to have some pretty thorough explanation as to how to work these problems. So your big payoff will be the 29th of January when you take the test and you see the same problem you've been working on. All right. If you've never worked on the problem, that test is going to be not a fun time. Okay, yesterday we spent, and most of you were here, so we spent the time working on this. I'm cutting and pasting on this 4.4. So you're not going to submit that one. You're going to eventually turn it in, but I'm cutting and pasting all the best of, like that's for 10. I'll cut and paste that out. And so all of that will be on tomorrow, probably tomorrow afternoon sometime that'll get posted. The rocket launch we were supposed to do today on the West Lawn, but late last night I watched the weather and they said 45-mile-an-hour winds, and you cannot launch a pretty light rocket in 45. It gets blown everywhere, and you get terrible data. We've done it before. So I'm going to wait. There's no rush on this rocket launch. I'm going to wait till there's a good day. I think the best day right now is looking at next Tuesday. Okay. But you'll know it after it happens. I'll take some video. Okay, that's from the launch stuff. That's the launch stuff. Let's go to that. Okay, now today's physics. So we're going to talk about this frying pan. Let's see if this works. Okay, this is a video. Maybe. Oh, here we go. Watch. So, okay, so watch. I don't know if the sound will come through. May or may not. Sound may not work.
If you hit the speaker button at the top right that has the slash through it, it'll play sound.
Oh, thank you. Boom. All right. A zoom point there for pointing that out. Okay, so anyway, I was washing the dishes last week, and I happened to knock. I think it was last week or before, and I happened to hit that when I was putting a dish up, and it started doing this. Okay. So I sat and stared at it, and then I did it again, and then I did it again, and then I did it again. I kept watching it and then timing it with my phone. My wife came in and thought, "What are you even spoken?" Staring at you're staring at, but it's physics, right? So then I filmed it, and I thought, okay, see it going, see a way that's rhythmic like that? That is a type of motion. And so we've talked about flat motion. We've talked about motion up and down an incline. We've talked about free falling, throw something up, it come back down. We've talked about circular motion. Here's another kind of motion. You start with the observables. You see what you can see, and then you come back, and then we're getting ready to go into what causes that motion. We talked about inertia, but let's talk about forces. Let's talk about, energy. Let's talk about the power. Let's talk about torque, all that stuff. But we got to first understand the motion. And so this motion today and probably tomorrow's topic is this oscillations, the way that oscillates back and forth. Okay. So in class, let's go back to class. So in class, we started looking at springs. I didn't have my frying pan up at school, so we looked at springs. Here. Jeez, easy. All right, so we looked at pendulums. There's a spring. See the spring there? We pulled the weight down, and the spring goes back and forth. Tonga, tonga, tonga. We looked at this big truck spring. We looked at the pendulum. We looked at the wheel. And so we spent the hour. The essence of the hour was looking at oscillating motions, okay? And then plotting it. We had to plot it on the board, and then writing an equation for it. That's the things we're trying to get today. If we can get the plot of these and then talk about the concepts involved, then I'll be happy. Okay, so I have animations as well. If you go to, this is 4.5 is sort of where we're going today. I don't know if we're going to get that far, but we're pushing our way towards 4.5 in your packet. But before we do that, I have animations, and on your home, okay, in the there's a module, And on the About This Class, there's a GIF module there where I have about 60 GIFs. And you can click on one of those and it'll take you, well, there's ones on Simple Harmonic Motion. You can click on those. It'll take you to these things, you know, springs going back and forth, back and forth, back and forth, little animations. I don't have that queued up. I was kind of thinking we were doing rocket launches. But anyway, I'll queue that up the next day or two and we'll watch that. But what we ended up doing is we ended up looking at circular motion because first I did this. I pulled the spring down and let the object go up and down, up and down, up and down, like on a spring. We watched that for a while. Then we talked about it. Then I did a pendulum, and then we lined up. We synced the pendulum to the spring, so that when the spring was at the top, the pendulum was all the way to the left. When the spring was at the bottom, the pendulum was all the way to the right. Now on a pendulum, you can see it here. I'll blow this up. On a pendulum, this right here is called a bob, B-O-B, bob. I don't know what. Oh, I know, because plumb bob. There's something called, not SpongeBob, plumb bob. And plumb bob, if I want to find out, there's history to all this stuff. But if I want to find out what is down, this is from my Apple Watch. But if I want to find out what is down, I hold something like this, and whatever way it's pointing, that's down. That's called vertical. For this, where I'm at, my vertical in Norman is not the same vertical as it is in Oklahoma City, right? Because believe it or not, the earth is curved. So this thing goes back and forth. Okay, you're getting sleepy, but this thing goes back and forth. That is the pendulum we're talking about. Simple harmonic motion. Simple harmonic motion. Your eyes are getting, okay, hold on. Some people are very susceptible to being hypnotized. I am one of them. I just all of a sudden go out. So that, if pendulum motion, we match that up. And I'm sorry, I have a video of this somewhere, but I can't, I have to find it. I'll find it tonight. That is matched up with this spring here. If you can see it, there's a spring. Let's go yellow. Okay. There's a spring here, right here, that's going up and down. So as that spring goes up and down, the pendulum, they're both linked up. It's kind of like rub your head and pat your head and rub your, you know, it's weird, but they're both. So, and you use the same graph and you use the same equation to describe both of those motions. This fits into a category of motion called called Simple Harmonic Motion, SHM. And you will spend 1.5 chapters in AP Physics just studying Simple Harmonic Motion. In fact, the last chapter, chapter 15, is all Simple Harmonic Motion. Okay, that's how you'll end your year next year, but you bring in all the calculus and all the other stuff with it. Here, my job is to introduce it, you know, get you kind of used to it. Okay, but that's not what we plotted. We could have, but that's not what we plotted. We plotted, maybe we'll plot that tomorrow. We plotted this boss. Okay, this is called a boss. Boss, B-O-S-S, boss. It's called a boss because how trains work, how steam engines work. It's an old ancient term. But a boss, like when I was a kid, I busted up my tire and I hit a rock or something, and I took it to Malcolm. I grew up in Mayberry, you know, Park City, Oklahoma. And so I took it down to the mechanic, like right out of a fairy tale. I take it to Malcolm. Malcolm's this crusty old dude. And Malcolm didn't care for me much because I was always hanging around. So I took my bike to Malcolm. I was probably 7 or 8. He said, well, I said, what's the problem, Malcolm? He said, oh, you got a boss. You got a boss. I said, what? I don't have a boss. And he said, just give me the tire. So he did it. He fixed it. He put a new tire in, fixed it all, and went to go get it that afternoon. And I said, oh, well, thank you. I just grabbed my bike and walking home, right? He goes, hey, come back here. I said, what? He says, you owe me 2 bits. I said, what? 2 bits? What? I said, you know what 2 bits are? That means a quarter. So that's my boss story. So it's called, so I never forgot it though. Here I am 61. I remember Malcolm. That's called a boss. And it's a boss because if I hook it up and then hook a piston to it, that's the boss of the piston. I'll show you that later on. Get to machines. So anyway, so our job, what I told them to do, they had to go to the board and plot as this circle, as this wheel goes round and around and around, they had to plot the boss's position versus time. So I don't have an animation of it. I have a video somewhere. I just don't have it called up. If that, you can imagine the thing go round and round and round. If you had to plot that, going round and around, how would you plot that boss's position versus time? For one thing, it'd be 3-dimensional plot. I'm not saying you couldn't do it, but it would require computer graphics. It would require, and they do it. They do have these plots, but that's too much for you to go to the board on, or for you to on your piece of paper. So we're going to simplify it some. We're only going to look at 1 dimension at a time. So like if this is the boss, we're only going to look at, we'll make this the x-axis. We're only going to look at the x component. Here's my boss. The x component of where that boss is. So the boss is going round and around, but we only care about the x, like the x projection. So if I project that down to the x-axis, it's like, where is this on the x-axis at any given second? Where is my projection? Like a shadow. Like, in fact, we do this. You put a shadow above it, a light above it, turn off the lights, and it shows a shadow that goes back and forth. Okay, so you're supposed to now, on your piece of paper, plot for me, what will the shadow, what will the boss's shadow be? How will that vary on the x-axis given time? Now, what we did was we needed to quantify this. So let me give you some quantities. Okay, here we go. So here's a quantity for you. From the center of this out to the edge, this is 34 centimeters. Now we call that A, capital A as an amplitude, 34 centimeters. Then we measured how long it takes for this boss to go around and around and around, and that's called the period. And so what we this T with the lowercase p, and that means T, capital T as meaning a specific time, and lowercase p meaning it's periodic, meaning it repeats itself over and over again. So we got out our watches, our phones, and I said, okay, we're going to time this. But knowing that people have a bad reaction time, we had the boss go around and around 10 times, and then we divided it by 10. So when we did that, at least in third hours, when I remember, we got 11.1 seconds to go around 10 times. So we divide that by 10. So we're going to say 1.1 seconds is the amount of time it took the boss to go around all the way 360 degrees back to where it started. Okay, so knowing this, knowing the amplitude, knowing the period, you should be able to plot the X position of the boss. Okay, now this is where they went to the board. I could send you into the breakout rooms. So I'm going to send you all into breakout rooms and let you guys talk about it, talk amongst yourselves. Let's go 4 breakout rooms. I'm going to assign automatically and create. So there they are. And I'm going to open all the rooms. Okay. So now you all, I think, are in your breakout rooms. I think. And I don't know if you can hear me or not. You may not be able to hear me. So now in your breakout rooms, if you can hear me, talk about, there's 4 breakout rooms. Talk about how would you plot this? Talk amongst yourselves. While you're doing that, I'm going to do my own thing. Oh, hold on. Let me open up the chat. And nope. Okay. Oh, okay. Okay. One more. Move to join room 1. Yes. Okay, I'm in your room now. You all, what you're supposed to be doing is, I wonder, let's see. Let me see. I wonder if you guys can share a screen. It'd be kind of cool within the rooms, you know, that you share screens.
Yeah, I think we can.
Oh, okay. That way, like once we get good at this, then there'll be like a person in charge of the room, and they'll go on the next room. I'm just checking all the rooms out, and then we'll come back together in a few minutes, a minute or two. Breakout rooms. Let me join room 2. Okay, I'm just going around and joining the room. Ask for help. Oh, Eric said he's in room 4. Ask for help. Okay. Okay, so I'm going to go to Eric because he asked for help. I'm just going around. You guys are supposed to be kind of thinking about this together. It's a small group. Let me go and see what Eric wanted down there. Join.
Yep.
Oh, so Eric asked for help, and so I got a message to come join you guys.
Yeah. Basically, we just wanted the picture for reference, just because we kind of like just wanted to see it again.
Well, is it on? Can you see it?
No, we can't.
So when you're in your rooms, you can't see the overall shared thing. Okay,
No.
That's interesting. All right. Yeah, so that's fine. We're about to get out of rooms again. I'm just playing with it. Let me go check out room 3, and I'll be right back. And then we'll all come back together.
Okay.
All right. So now I'm in you all's room, and all you're supposed to do in these rooms are, it's more of a, maybe as we get going on this, you'll have like the people you want to be with. And then right now I'm just randomly assigning people. But when you're in a room, it's like going to the board in the classroom and it's good that somebody would take over and share and be the person that would share the screen. If you guys can do that, you have to have an iPad, I guess. Yeah, I don't know how we're going to do that, but then we could all kind of work together. That'd be cool if we can share. If we have I don't know. Anyway, so let's get back together. I just wanted to try. I'm keep trying to think about these rooms. So now I'm going to close all rooms and leave the breakout room. And so all the go ahead and come back. The breakout rooms will close. You hit leave room and the breakout rooms will close.
You're muted.
You're still muted.
All right, so Zoom does all kinds of stuff. When you go into breakout rooms, it mutes me, which is fine. So you guys can just talk amongst yourselves. And then we And then, but then the thing is that group 4 found out was they were trying to use the image to help them plot it, and you couldn't see the image. Like it's not shared in your breakout rooms. Okay, so these are all little things we'll get better at. But anyway, so going to the breakout room, the whole point is that it's like you going to the board. But then, and then I think you found that you could share, like somebody could be the leader and share. But then again, you must have to have an iPad. So I don't know. Worth messing around with. Okay, so now we're back together. Maybe you thought about it a little bit. And let's now look and see what that graph should look like. Done. All right. So here we go. We're plotting X versus T. So it's the way we've always done it. Where X, oops, hold it. Where X is the vertical and T is the horizontal. So X versus T. Okay. And I didn't get this far, but I'd like you to plot 3 times around, 3 of that boss going around 3 times. So this is X, this is T. The amplitude was 34 centimeters. Okay, so 34 centimeters. I'll make that 34. We'll call that 34. Right there. And we call that, it's X, but we call it A, capital A. 1, 2, 3, 4, 5, wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, it's symmetrical. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. All right, there's my negative A. It's called negative A. Negative A. Okay, and then, then you establish what's called an envelope. I didn't expect all this. I kind of gave them hints as they were at the board. So then you put your envelope as a dashed line. It does what an envelope does. It contains the function. So you don't do it solid, do it a dashed line. There's an envelope up here, and then there's the negative envelope down here, the negative side of the envelope down here. And all of these kind of motions need an envelope. All right. So that's your boundaries. Okay. Okay, I'll write it down. This is called an envelope. Envelope. Okay. And let's do 3 rotations. So we said it was 1.1 second per rotation. So let's count this up. We'll say every 10th of a second is a dot, maybe. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that'll work. So this is my first. There's my first. The end of my first oscillation or first rotation. And then I'll do it again. 1.1. Now we're at, so this is a 1.1 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 2.2 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, how about that? Worked out perfect. 3.3 seconds. Okay, so there's my time, and now I've got to fit my function in there. Now, someone describe for me what their function looks like. What do your all's function look like? I mean, did you plot
It's a sine wave pretty much.
Right. It's not that, right? It's not linear. So it's, you know what? It's not sine though. And that's something that we were plotting. If we're plotting horizontality, and it's not fair to you to tell you it's not a sine. It's actually a cosine, but you didn't know that. We weren't spinning it in front of you. We made a big deal in class that it's the x-axis we're plotting. And so we started the boss at the x-axis, at flat, like, you know, horizontal compared to the center of axial rotation. So it was on the positive x-axis. So actually, but what you said, you're correct. I'm giving you a point on that. You said it's sinusoidal. It oscillates back and forth. So if my boss is going around and around and around, I'm just plotting x versus t, not y versus t. But at 1.1 seconds, it's back to where it started. At 2.2 seconds, it's back to where it started. And at 3.3, it's back to where it started. Where is it halfway? Halfway between where it started, where it ended. Where is it the half time for each one of these? So I'll put this on here. We said TP was 1.1 seconds. So where is it halfway?
Is it every half TP?
Right, so it's going to be at the other extreme. So 1, 2, 1, 2, 3. When I do that, oh my gosh. Oh man. Okay, my little dots change when I do that. Tag on it. Whatever. Okay, so do the best I can. That's 13. I didn't know it did that. Okay, so it's right. I'm going blue. I'll go with purple. So right there is halfway. Okay. Oh, whoa. Yeah, that's right. So it's halfway. So at the halfway of a period, you're at the other side. Okay. And then the same thing here at the halfway point, which I'm giving up on counting dots. So put a, it's actually blue. I'm putting a blue dot halfway, blue, and then again halfway. Okay. Now, what some kids in first hour did is now they did this. They went, okay, that is wrong. But if it's worth 10 points, they probably would get 4. They get 4 out of 10 for that. Partial credit. It does show the back and forth, but remember, this is x versus t. And so the slope is the speed. And this is telling me that the object had a constant negative speed and then instantaneously turned around at a constant positive speed. And these are called diffraction points. And things with mass cannot have diffraction points. Light can have a diffraction point because it doesn't have mass. But if you have mass, you have inertia and you cannot turn around that fast. So no physical object could ever have this as this kind of sawtooth as its graph. So let's erase that. So we have to draw tangent lines. I'm going to draw some tangent lines here. Remember, tangent represents slope. So I'll do it in purple. My purple will be my tangent lines. We did this. This is what we did in class. So tangent lines tell me the slope. Tells me, in other words, the speed. Well, you go, that thing, that you have to see it in your head, I apologize, but that boss goes round and around like the second hand on an analog clock at a constant rate. So what do you mean your speed's changing? the speed is changing in the X direction and in the Y direction. But when you put them both together in a circle, that is omega. That's angular speed. The angular speed is not changing, but the linear speed is changing. So the slope of a line, or slope of a curve, and it is a curve, is called tangent. And so think of that, think of an object going in a vertical circle, my thumb, my finger here. Think of my finger going round and around. Obviously, I need to work on my presentation. I had it all figured out for live presentation, but then video, what I need is some kind of animation. But so with my fingers going round and around, my finger is going at a constant rate, but in the X direction, it's not. See, when my finger is up here, it's at maximum speed in the X direction. But my finger is coming down on this side or on this side, it's not moving in the X direction. It's moving mostly in the Y direction. So the velocity is switching back and forth between X and Y. Here I get in my up top and my bottom, I get a lot of X, negative X, positive X. But in the sides, I get no X. And so it's zero velocity on the ends. So my tangent line is flat. This is called scaffolding. I was a geophysicist, so we had to learn all this kind of scaffolding. We had to learn kind of the proper way of drawing, these waves, because we studied, all a geophysicist does is study the waves of the earth. Like, earthquakes, waves. So this is flat. The tangents, the scaffolding is flat. So my graph should be flat on the ends, not pointy, not like a diffraction, flat. Now if it's going round and around, the pin, let's say, is going round and around, where is the pin going the fastest sideways? The fastest. Where is the sideways motion of the pin the greatest? Okay, I can't keep doing this too long. Where's the sideways motion of the pin the greatest? I don't know how you describe that, right? Well, in this case, it's that when it's up here or down here, that's the greatest. Over on the side, there's no sideways motion. It's up and down, hardly any. So the greatest speed, and we call that a POI, the point of inflection. The point of inflection is halfway between maximum, and then the negative maximum. So that is right here. My tangent is steepest. My tangent line is steepest. See, I'm drawing scaffolding. So my tangent line steepest between maximums and minimums. Maximum, positive max, negative max. What am I doing? Dumb. Ignore that. Oh, I thought I was off. I was off. It should be down here at the equilibrium point. This, by the way, is called equilibrium. So maximum negative, maximum positive slope, maximum negative slope, maximum positive slope, negative slope, positive slope. Now I have enough scaffolding that I can plot this. I've got to be at 0 at the ends, flat. So it goes from flat up to maximum slope, back to flat. Okay, same thing here. I'm off a little bit on that scaffolding. And I'm embarrassed. It's terrible. It's terrible for a geophysicist anyway. One thing a geophysicist you're able to do is draw waves. It's been a few years. Okay. So let's keep going. We're drawing 3 oscillations. Once we figure out the equation for this, then we're done. But let's finish drawing our, notice this is a cosine wave. It just happened to be a cosine wave, but it's really a, this is terrible. It's really a cosine world. Things are mostly cosine. Sine, for sine waves, usually you've fabricated it, or you put it into a non-inertial reference frame. It's cosine is what you normally do. Like on a pendulum, if a pendulum's at equilibrium position, if the bob is sitting there at the ground state, it's not going to do anything. It's not going to spontaneously start to go back and forth. You have to give it amplitude and then let it go. Well, if it has amplitude to begin with, like here, that is a cosine wave. Okay. So now we have to, that's the sketch of three rotations. And we're only looking at the X. We could do the same thing in the Y. It'd be 90 degrees out of shift. It would shift 90 degrees. And then Jacob, who used to be virtual, now he's in the class, but he came up to me at the end and he said, so if you were to plot both, like X and Y through time, he said, would that corkscrew? I said, exactly. Yes, that would be a corkscrew. And you can look those up, animations of corkscrews. Corkscrew is how the Earth goes through the Milky Way. The Earth corkscrews through the Milky Way. Corkscrew graphs is electromagnetics. That's how light works. Light moves, quote, moves from our perspective through space in a corkscrew manner. Because electricity is one way, magnetism is another, and light is a combination of electricity and magnetism. So it corkscrews. When you put polarized glasses on, you're only looking at part of the corkscrew. It filters out the other stuff. Anywho, so now we have the equation. Last thing, I got about 6 minutes here. So the equation x of t is equal to something, something, something. Somebody help me out. Give me a word. Give me something. Shout it out. I got it. Cosine. So I'm going to shout out. So good job. So there's a point there. So cosine. I don't know if that was Miranda or that was Sophia. You guys kind of sound the same when you first talk. It doesn't matter. You assign the point. So cosine, and we got to put the amplitude on there. So it's A, which the number wise that'd be 0.34. Cosine what? You don't take the cosine of time. I don't say, oh, it's 3 minutes. What's the cosine of 3 minutes? I don't know. You don't take cosine of distance. Like in math, you learn cosine x. I understand why math does it, because x in math is just a generalized letter for any variable. But you would never say that in physics, because x means something. X means position. Delta x means change in position. I don't say what's the cosine of 5 miles. So that's nonsensical. So we don't put an x there. We don't put a t there. We take the cosine. You take the cosine of angles. You take the cosine of a delta theta, right? But that's not right either, because the equation has to be a function, see, right here. It has to be a function of time. Now, what's the relationship between theta and time? What's the relationship between delta theta and time? What puts those two together? What connects these two? Anybody want to throw it out there? Omega. Thank you. There's another point. So omega, way back, the old baby's bottom. omega equals delta theta over T, right? So omega plays a role here. It's the change in angle over time. And so if I want to, so delta theta then is omega times T. And so I can erase this because that's not going to help me. I erase this and I make that omega T. Now, that is a very simple, no phase shifting, nothing like that. A very simple, we've learned our first simple harmonic motion equation. That's sort of the standard equation in simple harmonics. Maybe we'll make these purple or something because no one's really hung these from the ceiling. We ought to. Oh, no. We did last year. We did it. I have it somewhere, but it doesn't help you, does it? Anyway, in our equation sheets, we'll add these to it. And somebody asked if I could make a PDF of those equation sheets so they can print them off nicely. I'll do that. I'll probably try and do it today if I can. Okay, so we learned a lot. Hope maybe you already knew it, but let me highlight that now. Knowing how to do the graphs and knowing how to do the equations is huge because probably 75% of physics is waves. A study of physics is waves. Any quantum, any gravity waves, everything's a wave. Remember that? De Broglie, if you're into chemistry, in the 1920s showed that particles and waves it's called particle wave duality. You're both a wave and you're a particle. We're both. And so waves, understanding sinusoids and simple harmonic motion is huge in your oscilloscopes and stuff. And also in chemistry and biology, harmonic oscillators in biology, Brownian motion. In chemistry, all molecules have vibrational modes and they're basically simple harmonic motion. Okay, and in quantum. Photons, we talked about the other day. Photons are waves. Okay, so we'll explore this more tomorrow, and we'll look at 4.5 mostly tomorrow. So tomorrow the sheet is 4.5. This was sort of an introduction, but it's in the standards. I've got to talk to you about waves and vibrations. Okay, you guys were a great audience. Thank you very much. Let me stop the sharing. And I think, yeah, we're still recording. So I'll see you guys Friday. We're going to go usual Friday. Last semester, we didn't do Fridays because I would be out riding my bike, but it's just too cold now. And I did ride my bike yesterday. But so we'll do 5 days a week. Now, the 27th, it may slightly change a little bit because of this flex day. Not going to affect us much. Okay. So work on those practice problems. I want to see you guys on Facebook. Oh, and also, even though you're not turning it in, you're not submitting it yet, go ahead and work on 4.4. I'll post that key tomorrow. I'll post the key to 4.2 today. All right. See you guys tomorrow. Bye-bye.